Hello, welcome to Lesson 12, Unit Hydrographs of CE5361, Surface Water Hydrology. And on the screen is the typical starting page for the lessons. So there'll be this picture, and the next page goes to the lesson resources. So you should watch this video before completing the lesson, and this link takes you to the content page. The video link is under lesson materials in the MP4 source, and there'll be a link to this YouTube video. Some of the other things in the content page are the script files. I've already uploaded this set to the share space. We'll use that in a minute. And the PowerPoint I'll be drawing from, I've already downloaded, is lesson 12. Description for the lesson is: the lesson presents the theory of analysis of rainfall and runoff data to obtain an estimate of a transfer function. Once the transfer function has been developed, it is used with both design storms and measured rainfall hydrographs to compute the expected runoff. Expected in the sense of anticipated, not expected in a statistical sense. The resulting runoff hydrograph is then used for design purposes. Unit hydrographs are one kind of transfer function kernel that can be developed for a specific watershed or for general use on watersheds where data are not available. So a specific watershed unit hydrograph requires a set of rainfall and runoff data for that watershed, and the preparation of a unit hydrograph from that is called analysis. So that's unit hydrograph analysis. So we analyze the rainfall runoff data in the watershed to develop a unit hydrograph. In the absence of that, if we're going to synthesize a unit hydrograph from watershed properties such as area, slope, land use cover, that's called synthesis. And that's used in the case where we don't have observations of runoff, so for ungauged watersheds. The conceptual framework is typically separation of rainfall into excess and non-excess components, so that's application of a loss model, and then separation of runoff into two parts, direct runoff and base flow, and identification of the unit hydrograph as the transfer function. So without much further, we'll go take a look at the available reading materials. So there's Chow-Maidment Mays, pages 201 to 241. There's the Highway Hydrology Manual, pages 61 to 631. These two both go into some detail on unit hydrograph, and in fact, much of the examples are taken from Chow-Maidment and Mays or modified from that, some from the Highway Hydrology. I've included a few other useful readings. One is Sherman's original paper from 1932. I'll verify that it's there. It is. Called Stream Flow from Rainfall by the Unit Graph Method. You should read that for having a history of the method as it applies today. The second one is by Lienhardt, 64, where he presents the dimensionless unit hydrograph as a statistical mechanical structure, and actually using Maxwell-Boltzmann speed distribution to understand the behavior of the hydrograph. It's remarkably interesting. And then he has a second paper, 72, which is literally less than a page, that references back to the 64 paper. So this is included for historical completeness. So let's move on to the presentation, if I can find it. So it's already downloaded. There we go. Unit hydrographs. The readings we've just gone through, and Chapter 12, Stream Flow Response at the Catchment Scale in Bruce Hart, Hydrology, Cambridge University Press, the Kindle edition is the other main reading source. So these two readings right here, if you're unfamiliar with unit hydrograph theory at all, this would be a good place to start, and actually the top reading on this page. So let's begin with an idealized hydrograph. So a hydrograph is a plot of paired time discharge values. And the act of plotting is irrelevant. It can just be a collection of time and discharge or time and stage at a location. That's called a hydrograph. And the idealized hydrograph has four portions, as indicated here. There's a preceding portion until the runoff begins, and then it begins to climb. That's called the rising limb. And then it rises up to a peak, which is cryptically called the peak flow. And then there is a descending portion called the recession limb, where it comes back down to the pre-storm conditions. Excuse me. On the recession limb, there's a place where the function goes from concave downward to concave upward, or the second derivative up in here is less than 0, and the second derivative here is greater than 0. And where that transition occurs is called the inflection point. I have it drawn up here on the diagram, but on different hydrographs it will appear in different points on the recession limb. There's also a component prior to the storm and after the storm where there's still flow. That is called the base flow component, and that's flow that occurs in absence of a storm. Perennial streams, streams that have year-round flow, will have a base flow component because they can flow even when there's no storm in recent history, recent being days, weeks. Ephemeral streams are streams that don't flow year-round, and often their flow is associated only with storm flow. And in those cases, the base flow component might be assumed to be negligible. If it's not negligible, for the analysis part, we would want to separate the base flow from the direct storm flow, because the unit hydrograph transfer function is not designed to be able to accommodate base flow, at least not as usually presented. There's several methods for making that separation. One depicted here is the constant discharge method. So when the rising limb begins, we declare the value of flow just before it rises as the constant base flow, and we essentially extend a horizontal line from that point until it hits the recession limb again, and declare everything above that line, in this case the rose-colored area, as the storm flow. The second method is called the constant slope method, and again we start at the same point on the rising limb. In this time we extend a line segment to the inflection point and declare everything above that the storm flow. This is fairly difficult to implement in multiple peak hydrographs, implement algorithmically, that is. If you're doing them by hand, the human eye can quite quickly make these kind of drawings, but teaching a computer to do it, not so easy. Another method is the concave method, where the preceding slope is extended to a point beneath the peak flow. At that point, we go from that location to the inflection point and declare everything above these two line segments as storm flow. This too would be challenging to implement in an algorithmic sense for automated application. There's a couple of other ways to do the base flow separation. The master depletion curve is a basin scale approach, and in that the behavior of this hydrograph in the absence of storm flow is studied, and a decaying exponential model is usually applied at the basin scale. And so from the beginning of a water year, we know what the base flow would be in the absence of storms, and we use that as the base flow signal to separate for doing the analysis. It's not that easy an approach. And then continuous simulation techniques is kind of a variant of that. So a swim could be applied at a watershed scale. Presumably, I suppose HEC-HMS could too. And we simulate several years of behavior with known data, and that's used to establish what base flow will be at any instant, and then that can be separated from the storm flows. For practical cases with multiple peaked hydrographs, the constant discharge method by far is the most straightforward to apply and probably is the most used. It's non-ambiguous, so it's fairly straightforward to implement repeatedly. So the topic of unit hydrograph, there's 4 important questions that come to mind, which is what is one, how are they used, how do you make them, and how do you make them when you don't have gauge data. So first, what is a unit hydrograph? L.K. Sherman, 1932, is credited with a seminal publication on the concept, and that's on the server. You can read it, and even actually use the terminology unit graph. What the paper does not contain is pages of typeset mathematics. It took hydrologists a couple decades after his paper to figure out how to take a simple concept and apply mathematics to make it uninterpretable. It's used to explain the redistribution of excess precipitation on a watershed. It represents the response of the watershed at the outlet to a unit depth of excess precipitation. And actually there's a unit time concept too. Use of the word excess implies that some kind of loss model is applied to the raw precipitation, and the time redistribution implies that some kind of transfer behavior is applied. So taking raw rain to produce excess, we apply a loss model. Taking the excess uniformly distributed over the watershed and moving it to the outlet, and then converting it from a depth into a discharge signal is the transfer function. And that transfer function with certain properties is called a unit hydrograph. Let's look at a related concept that I hope will illustrate the idea of transfer function and relating inputs and outputs. Imagine a watershed as depicted here. In this case it's rectangular, but there's known watershed area. There's precipitation coming in as the little red arrows. The product of that precipitation signal and the area is the inflow to that tank. This tank has no losses, so nothing leaks out the bottom, nothing evaporates. So we have inflow minus outflow equals 0, or inflow equals outflow. But what doesn't happen is those don't happen at the same time. So that inflow comes in and immediately is stored, and so the depth times the area at some instance has to equal the inflow. And if there's no outflow, then that depth is going to get bigger and bigger. And now we have an outflow model that says that outflow is equal to some function of the accumulated depth. So if depth starts out as 0, there's no outflow. As soon as inflow comes in, the depth increases. This number increases, it produces outflow, and then that reduces the storage, and so on. And we can apply a differencing scheme to that to approximate the behavior. So ignore the first bullet item because it's wrong. Our tank outlet is a rectangular slot, and we're going to start with it as different widths. 4 foot wide, 5 foot wide, and 1 foot wide. The outflow rate is determined by the depth of water in the tank at any instant, kind of like a classic time to drain problem. And the formula for that is shown here. If you look at that carefully and you remember your open channel hydraulics, you'll see that we're simply stating that there's critical flow in that slot. And so everything is governed by the depth and the width of the slot. Whether that's true in a real case is questionable, but it gives us a working model for the purposes of this discussion. Furthermore, we assume the water getting into the tank can get to the outlet without any delay in relative time. So presumably water can come in and get out in the same time interval, and there's no delay, which becomes more and more absurd as the tank gets longer and longer. As those travel distances get big, it's hard to convince ourselves that water can get out in the amount of time of a single time interval. And the precipitation depth is uniform over a time interval, and it's uniform over the tank. Okay, so there's our setup, and if we take that and analyze it, apply a simple mass balance to the tank, and then rearrange terms, we can come up with this numerical update scheme that says that starting with an empty tank, precipitation comes in at time t, and then that precipitation at time t produces a depth of t plus delta t, and then that depth of t plus delta t produces a discharge of t plus delta t. So what I've done is I've done a mass balance equation on the tank and the flow equation, combine them and put them back into the flow equation. So everything here on the right hand side, this is our transfer function, and the important thing is it takes input precipitation, input rainfall, and it produces output discharge. Now we've got a cubic here and a cubic here, and everything's in a square root, so this is probably not linear in any sense of the imagination, but it's less nonlinear than I would have thought. And then here's some simulations, and we'll look at the R script that made these shortly. So our first case is 4-foot outlet, I think. It says 6-foot outlet slot, but I don't think it's that big. And they're all laid out the same way. We have a precipitation signal in red, the outflow hydrograph in blue, and then in light gray, barely visible, we have the storage either in watershed inches or in volume in light gray. So we can see as the cumulative volume goes down, the cumulative runoff goes up. And this is correct behavior here. As time goes long enough, what came in is red should equal what come out as blue, because there's no long-term storage, there's no losses in these models. So here's a case of a 1-inch pulse coming in. Here's two 1-inch pulses coming in 12 hours apart. And nothing surprising there, except we see that first peak and decay, and then the second peak and decay. And then here is changing some of the behavior of the rain. Instead of coming in 1 hour, it's coming in as 0.75 and 0.25, and then 0.25 and 0.75. And again, our transfer function is keeping track of that and produces these responses. And the last one will change to a different slot, and what we expect here in this case is that the decay is much slower. It takes longer for water to get out of our tank, and so we have these longer tails on the hydrograph, and in the cumulative space we see the effect of change there. And so our function, if you will, is Q is some function of precipitation area, in our case initial depth, slot width, and any losses. And a unit hydrograph is simply a type of that function, a particular type of function. Let's go actually take a look at those. So I've gone to our share space, if you remember how to get to that. We log into that, and I've already moved the files there. Let me shrink that. And I want to launch my R script. While that thing's deciding to launch, let's go look at So here's our first input file. So it's in 2 columns, hours, precip, and so there's 1 inch, I'm using units of inches, 1 inch in hour 1, and then everything else should be 0. And let's go ahead and run the simulation. It's odd. So we'll open the file associated with lesson 12. And set the working directory to source file location. Turn that to 1. Let's quickly examine the script. So we have the outflow function, which is exactly that equation in the PowerPoint presentation. So outflow width is the slot width. There's a discharge coefficient, which is used for turning dials. I believe it's set to 1 in this example. There's the watershed depth, and there's gravity, and the outflow is equal to the square root of the width squared, gravity times watershed depth cubed, just like the formula. And the inflow function is precip times area, and then the change in depth is essentially the storage equation. Well, it is the storage equation. Inflow minus outflow equals change in storage, and then divide by the area to return that as a depth. And we have our aggregation function, which is used to take our incrementals and make it cumulative. And then here's the actual simulation, this physical size. You can look at that and see that's an acre. The outlet width at this point is set to 1. Let's move it up to 6. And I'll modify the plots so that, there's what I was looking for. Trying to figure out which plot's going to look better. And we'll run the script. And unfortunately, it doesn't have enough real estate. Let's try them side by side. Okay, so I'm doing R script here, not so much hydrology. Oh, that's better. And the only thing I need to do is get the ordering. So I want to move this plot. I'll leave it like that. So this is the opposite order in the presentation. The presentation, this figure was the one on the right, and this is the one on the left. Okay, so here's our first case. Let's see what happens when we double the input rainfall. Now we would expect the accumulated volume would be double. So we're probably at around 3,700. So twice the 3,700 would be around 7,400 if we were to double the input. How do you double input? We simply do that by changing the contents of the precipitation file. Change this from a 1 to a 2. And let's see what we expect to have happen. We expect that red line to go up to almost 8,000. Same with the blue. We expect that line to double in height and that line to double in height. And almost sure enough, except we have too much outflow, and that's a consequence of the numerical method that we used. We change the width to 4 and redo it, and we'll work correctly. So that one doubled, and that indeed went to about 7,400. We'll leave this at 4 until I break something else. Okay, let's look at a different precipitation vector. So notice no change in watershed properties, slot width of 4, different precipitation vector, and then here's our responses. And I forget what the third one is, but we'll see in a second. And there's our third case. Now let us, instead of having an outlet of 4, let's make it a 1. So it's 1/4 the width, so it would be probably 1/16 the performance. So what do we expect to have happen? Instead of this one achieving equilibrium so quickly, we expect it to take much more time. So these are going to have much longer tails. And indeed they do. Remarkably, it actually is getting to equilibrium in the 48 hours. I'm surprised at that, didn't expect it. And there's our precipitation 2, and there's precipitation 1, which I think still has a height of 2 because we changed it. Okay, so that's the idea of our transfer function. It turns this red, you notice the red signal didn't change between the 3 files, only the blue changed, the hydrograph. And so that transfer function is our hydrograph function. In this particular example, it's nonlinear by the nature of its construction, and sadly it's very sensitive to choice of outlet width, and that's because of the numerical scheme we're using. We're using a simple Euler approach, and if we provide input conditions such that the outflow rate is too big, I mean bigger than the volume of the tank, it completely drains the tank to empty and beyond. It will drain it to negative depth is what I'm trying to say. And down here in the code somewhere is something to yeah, here we have it set. If the depth gets less than 0, just store it as 0. If we were to turn that off, we could see the effect of negative depths. That would also produce negative flows, which I think would confuse the heck out of everything. Okay, so that's our introduction to that, and one thing to do, we'll go back and change that to the original condition. Good. All right, we'll return to the presentation. So you've seen the value of the functional approach. Now, we built that based on a simple geometry and applied principles we had back in fluid mechanics. So the unit hydrograph approach takes those broad concepts and gives us a way to apply that for a watershed. So let's look at what a response model does. We have input precipitation, which I've coded as red, and we have output discharge, which is coded as blue. And in our watershed case, the watershed processes that red signal to produce the blue signal. So here's our input signal, here's our output signal. And the things the watershed does is it imposes losses, storage, routing, and transformation. In the example with the tank, there were no losses. The storage was uniform over the entire watershed, and there was no routing. So everything could get to the outlet based on the flow rate determined entirely by storage. And the result was our transformation. Another way of looking at what I just described is that the response models convert the excess precipitation signal into a direct runoff hydrograph at the point of interest. So rainfall comes in, a loss model is applied, losses are abstracted, What's left is the excess precipitation, and then that goes into our response function to produce the runoff. The response function is the unit hydrograph. Here's yet another picture of the same idea. Precip comes in, hits our watershed here, which looks like a tank with a pipe in it. A portion is lost, and what's left is the magenta, and that appears as runoff. If we look on the precipitation signal, the precipitation pulse has a pulse length of d, called its duration, and we could stack these in time to the right, and so we can have a whole bunch of different pulses. We saw an example of that with the tank model where we had those two inputs 13 hours apart. They don't have to be 13 hours apart. They could be right next to each other. But the unit response is for this single picture here, and we have to add everything together in time and convolve everything in runoff space to produce a direct runoff hydrograph. So let's go back to this single unit of width d. The loss model is applied, so of that pulse height, a portion is loss and a portion, the magenta portion, is excess. Then the unit hydrograph transfer function converts that pulse into this signal. And each of these increments is at an increment of d. And in discrete unit hydrograph construction, that's required, is that each ordinate on the hydrograph will be a time unit d apart. And the area under this curve and this curve are supposed to be the same. It's not apparent in the drawing because it's hard to draw it visibly for that to be true. There's a time characteristic called the time to peak, and it's the distance in time from the beginning of rainfall to the peak discharge. And there's something called the time lag or the basin lag, which is the distance in time from the centroid of the input pulse, from period, or d over 2 if you will, to the peak discharge. So T lag and TP are not the same thing, although they're certainly related to each other through D and through being the same watershed. And then there's a time base of the runoff hydrograph, here shown as T sub D. In this case it's 1, 2, 3, 4. This one's 5 time units, but it'll be different for different watersheds. So there's the runoff time base, and the length of this time base is related back to the original pulse length. So if the pulse length is different, this time base would be different for a particular watershed. The precipitation, the incoming signal, this is coming from the highway hydrology book, is typically broken into 3 components: an initial abstraction, which is a loss, and then the operational losses, which are shown here as losses, and then what's left is the rainfall excess. And so on this upper line is intensity plotted downward, which is a typical convention, and then times moving to the right. So here's our input function. The initial abstraction is accounted for, that never appears as runoff, and then the losses are accounted for, and then what's left is the excess. And so this excess is applied to a transfer function to produce a unit hydrograph, which is this unit hydrograph here, and then that is convolved to produce a direct runoff hydrograph, and when that's added back to the base flow, then this is the predicted response. So the unit hydrograph operates on rainfall excess to produce the direct runoff. That's important. And in this red arrow right here, what's not well articulated pictorially is that there's a transfer function process going on here. Here it's labeled, but that label should be moved up here. So let's look at excess hyedographs. So I've taken that hyetograph picture and redrawn it here on the left. The upper one shows the raw intensity, and then the loss curve removed here. And if we push all these remaining pulses, which are now excess, down to the intensity equals 0 line, this is our input signal for the unit hydrograph. The first time block there's nothing, second time block there's this pulse, this pulse, this pulse, this pulse, and this pulse. Now the idea of delay comes in. If the pulses could immediately get to the outlet, which in some sense they do in our tank model of a few minutes ago, if they could directly get to the outlet, we would expect the output hydrograph to pretty much look just like the input time series, except the units would change from intensity units to runoff units. And so our output response would look like these green pulses here. Red pulses in, green pulses out. However, the pulses are uniform over the whole area, so water particles that are close to the outlet are going to get out sooner than water particles that are far away from the outlet. Hence, there has to be some time redistribution or time delay, and that's what the unit hydrograph does. And with a time delay, our output response might look something like this green distribution here. And if we look at the beginning of excess, right there, the peak occurs over here, whereas if there were no delay, the peak is right here. No delay with delay. So the remainder of unit hydrograph analysis is how to get that green blob. So the unit hydrograph is the function that maps those excesses from the red pulses to the green blob. The total hydrograph, which is often what we're ultimately interested in, is the algebraic combination in time of the direct runoff hydrograph, or green blob, and the BASEFLOW hydrograph, in this picture shown as magenta. And that produces this blue line here, which is the direct hydrograph. There's also terminology called a direct runoff hydrograph, which often refers to the green blob part. It will usually be obvious by context. So the direct runoff duration is the same for all uniform intensity storms of the same duration. These are unit hydrograph properties, it says assumption. So any storm of a particular fixed duration will produce a direct runoff duration of the same fixed duration. Two excess hyedographs of the same duration will produce direct runoff hydrographs of the same duration, but the runoff rates are proportional to the volumes of the excess hyedographs. That may be hard to picture. If we have this excess hyetograph, these red pulses, it produces this green blob. If we have another excess hyetograph that has the same pattern as this, but everything's 3 times as tall, the green blob becomes 3 times as tall. Everything is stretched in the intensity direction or the runoff direction by 3. That's what that second statement means. The time distribution of direct runoff from a given storm duration is independent of concurrent runoff from prior storms. That's a way of saying that there's no memory. Our tank model did have memory, so the unit hydrograph doesn't have memory. What that means is if we produce this green blob here, and then there's an identical storm that starts right at the end of this one, there'll be another green blob over here, and the 2 green blobs will add together. The no memory assumption. Okay, so we'll look at those in turn. Direct duration is the same for all storms of the same duration. So here's duration red, produces runoff duration green. Here's duration also red, runoff duration green. The 2 excess hyedographs, the same duration, will produce direct runoff hydrographs, the same duration, but with rates proportional to volumes. So here we have red duration, produces green duration, red duration same, green duration same. But now the heights of these are different, and so the area under this one is different than the area on the right so everything is stretched in the vertical. And the key thing is that the integral of the precipitation signal multiplied by the watershed area, so that's the volume in equals the volume out. This lowercase q is in units of watershed depth. And the time distribution of direct runoff is independent of concurrent runoff from prior storms. So here's storm 1, produced this light green blob. Here's storm 2, produced this light green blob. Storm 2 receives no memory information from storm 1. They're just placed on top of each other in time and then added together. And so the net runoff hydrograph looks like this twin blob here. Each unit hydrograph has a particular duration associated with it, capital D in the diagram. And that duration needs to coincide with the time step used in discrete aggregation. Another way of saying that is that a d-hour unit hydrograph is the response to a d-hour pulse of excess precipitation. So, for example, if d represents 1 hour, a 1 hour unit hydrograph is the response from a 1 hour rainfall. Now that 1 hour unit hydrograph may produce several hours of runoff. So there'll be an hour 1 runoff value, an hour 2, an hour 3, an hour 4, an hour 5, and maybe that's all there are. And so that 1 hour input pulse produces 5 hours of runoff. The flow associated with that response is reported every d hours until there's no further response. That's T sub d in the diagram. And we got to go back to the diagram that refers to. It's T sub d in this diagram. So here's our 1 hour input. Here's our 5 hours of response. Every watershed has a characteristic response time, T lag and TP in that diagram that we just showed. Those response times are thought to be physical properties of a watershed. And the characteristic times are related to things like contributing area, slope, cover. The time step for aggregation must be the same as the duration, meaning that 1 hour hydrographs needs to be done on 1 hour pulses produce hydrographs that produce responses every hour, and you need to stick to the 1 hour time increment to produce your time to peak estimates and so forth. If you use longer time increments, you get a mathematical property called aliasing. There's tricks to use shorter ones, and failure to keep that in mind when you're doing them by hand or by your own code can create some interesting errors. For example, if you use a 2 hour time step but it's with 1 hour hydrographs, you're going to miss the peak because the peak will occur in the middle of one of those 2 hour increments, and so it'll be averaged. Ultimately, that process, when we added the 2 hydrographs together, this is called convolution. So hydrograph 1 is convolved with hydrograph 2. Another way to think of convolution is its superposition in time. If we write it in a continuous form, the watershed inches per unit time is equal to the convolution integral of 0 up to some time t. R is the rainfall input of tau. F is our hydrograph function, t minus tau d tau. So this is an interesting notation because the variable of integration is tau. The functional form is t, and we're integrating from 0 to cap t. It's a definite integral. And so as our discrete times change, this value of t changes, and we get, well, ultimately we can recover an entire functional form. In discrete convolution, the notation is just as confusing, but when we go ahead and draw a picture of the matrix in a second, it makes a whole lot more sense. Discrete discharge, Q at each particular time interval, 1 hour, 2 hour, 3 hour, is equal to the unit weight, so that's just a weighting value, times the precipitation at the mth interval, where m runs from 1 up to n, where n is less than or equal to cap m. Let's look through an example because that will illustrate some of these ideas and it clarifies some of that notation. Here's a example from Chow, Mabit, and Mays, page 216 to 223, and it uses a method called back substitution. Here's our time intervals. Well, assume these are in hours, so at hour 0.5, 1.5, we have 1.06 inches of rain in that first half hour, 1.93 in the second half hour, 1.81 in the third half hour, 0 elsewhere, and the observed flows are 428, 1923, 5297, 91, 31, 10, 625, and so on. So these three inputs of rain produce this observed runoff hydrograph. What we want to do is find the transfer function that produced that, because once we have the transfer function, we can change what the rainfall signal looks like and compute what the new flow signal will look like. So here's the discrete convolution laid out in a matrix. So the discharge in time interval 1 is equal to the precipitation in time interval 1 times the unit weight of 1, whatever it is. Precipitation in time interval 2 is equal to the precipitation in time interval 1 times the unit weight for 2, plus the precipitation in time interval 2 times the unit weight of 1. Runoff in 3 is precipitation 3, unit 1, precipitation 2, unit weight 2, precipitation 1, unit weight 3, and so on. And this matrix is constructed moving downward, and it moves to the right depending on how many non-zero rains there are. A more convenient way to express it is in this vector and matrix form. So here's the precipitation array, here's the unit weights, which we don't know yet, and here's the right-hand side of observations. And if we put all that into, in this case it's a spreadsheet, we'll show you an R script in a minute. Here's the observed values, and here's unit weights that are produced by guessing a value of the unit weight, calculating the discharge, computing the difference, and then adjusting the guess until the difference is small. And so this column right here is the unit hydrograph column made by this back substitution technique. So for example, unit weight 1 is Q1 over P1, which is 428 over 1.06, which is 404. Ultimately, I guess 403.77. And that produced an output of 428, which is correct. And then continued so on, back substitution to construct the spreadsheet. If the system is full ranked, as it is here, you could just solve the resulting linear equation for the unit graph weights. And in Excel, that would look like this, but Excel may not be the best tool for this, especially if those time series are more than 15 or 20 inputs. You want something a little bit more, actually less graphical. You want something that can operate on the time series. And we'll go take a look at that right now. So let's go ahead and take a look at this example and implement it in our script. Yeah, that's the summary. So we'll escape that, and we will go to our online environment, which has already been prepared. So I guess we've got to restart R again. R scripts, lesson 12 scripts, unit hydrograph example, and we'll open that up. Set the session to source file location. And before I run it, I'll show you one of the attractiveness of the unit hydrograph discrete convolution. So here's a script that analyzes that whole hydrograph. So we read in a table. We'll go take a look at what the table looks like. Hours P and Q. So 0.5, 1, 1.52, 1.06, 1.93, bunch of zeros, 428. This is exactly the information that was contained in the 3 columns in the spreadsheet. So we read it, figure out how long it is, we produce a Q vector. We don't need to do that, it just makes naming a little easier. A unit hydrograph vector, we start out with nothing but zeros, so we don't know what it is. We create a precipitation matrix. We populate that precipitation matrix. We then solve the linear system to recover the U vector. We print the vector just because that's interesting, and we're going to make 3 plots. And so given our real estate, we'll do it this way. I'll do 1 plot at a time, and then we'll modify it. So there's our first one, the precip. There's our discharge. And last one is the unit hydrograph. And if we look down here, there's the computed unit hydrograph. So the advantage is when we want to provide a different rainfall signal. We'll do that in a second. We won't do that in this video. We have to modify this code to take the case where we know what a unit hydrograph is. What does the new response hydrograph? That's the next lecture. And let's go ahead and make this so it shows everything at once. That's kind of cool. And if we want to stick to my picture convention, this chart, I think my convention is blue. And I don't have a transfer function convention for color yet. Let's use magenta. I love to say that word to be a good name for a person, although I think it was a name of a character in Rocky Horror Picture Show. And there is our result of that unit hydrograph analysis. So here's our unit hydrograph that says that 1 unit of input rainfall, so 1 inch over a 0.5 hour period, will produce the following. At hour a half, it'll produce a little under 500 CFS. At hour 1.5, a little over 1,000. Hour 2, just shy of 2,500. Hour 2.5, 2,500. Hour 3, down to 1,500. And so it'll produce this waveform. If there's a second one coming in, it will produce 2 of those convolved. Our next lesson, we'll go ahead and extend these ideas and actually do the convolution so we can see the utility of the unit hydrograph. Let's return to the presentation, and I think we're ready to conclude. So that our script does the same thing as this spreadsheet. Just to summarize, unit hydrographs map the excess precipitation signal to the outlet. Baseflow separation, if necessary, is done ahead of time. That isolates total discharge from the storm-produced discharge. Loss models are implicit in this method, so it's implied that losses have already been accounted for. And the unit hydrograph only operates on the excess to the outlet. Back substitution, or the linear equation solution method, was illustrated to obtain a unit hydrograph. So as it is, we're only part way there. We only have a way to get the unit hydrograph from data. Our next steps will be to use that unit hydrograph on different storms, so we can do what if, and then the next step will be how to synthesize or construct a unit hydrograph in the absence of data. So we construct it based on correlations with things like watershed area, slope, where in the world it is, what the cover is. So that concludes lesson 12 of ce5361. Go ahead and go into your Moodle site, log in, and complete the actual lesson. We'll take a couple seconds right now to do that. I guess we'll do it here because I think we're already logged in there. Yeah, there we are. There's our lesson. And so now this is what you would do in that case. We've watched the video, or if you're at this point you have watched the video. So there's the readings, more readings, idealized hydrograph. We've seen that presentation, baseflow separation, different method. And now a question. Baseflow separation is required for hydrograph analysis on soda streams. That sounds silly. On video streams? No, has nothing to do with videos. On perennial streams? Perennial, those are all the time, maybe. On every stream? Well, of course not. The fact we're even asking this question implies that that's not the right answer. On ephemeral streams. A perennial stream always has flow. Ephemeral is sometimes has flow. We know for sure we're probably going to have to do it on perennial. Maybe on some ephemeral, but not all of them. And it tells us we're correct. We can continue. What is a unit hydrograph? How are they used? Go through that. We're presented with a picture of Sherman's paper and the concept of excess. A series of our tank models, response model, several examples. And this slide didn't get enough love. This is probably the most important one because it has all the timing terms. Keep that in mind as you're working through your own lesson. Now has a question: what is a unit hydrograph? A measuring instrument that records the hydrograph from a watershed of 1 acre? Well, no. Unit hydrograph is not an instrument in the physical sense. A type of response function? Well, that sounds kind of right. It's a response function. Represents the response to a unit depth of excess precipitation over a unit time interval. Yeah, that sounds pretty good. Let's look at the other two just in case. Converts the precipitation signal into a direct runoff hydrograph at the point of interest. Close, but this doesn't say anything about excess, and this is direct runoff hydrograph, not the storm component. A type of response function that represents the response of the watershed to a unit depth of precipitation over a unit time interval. That sounds good too, except we're looking for the word excess. So excess is important. We can continue. Then we'll go through these series of slides. Curious what this looks like on video at a 5 frame a second frame rate. It has some of the properties of the unit hydrograph, if you recall that. The continuous convolution integral and discrete convolution summation. And it begins our example. Okay, so that pick up where you left off is handy if you click the wrong button like I just did. Next page. There's the precipitation array. There it is in vector matrix form. There's a back substitution process by hand, and the R script did it by linear algebra. We'll discuss a trick to handle the cases where the system's overdetermined. That one worked because we had 13 rows and 13 columns. The summary, and I think we have one more question. Good. So it wants to match the variables with the descriptions below. So T sub D, if you recall, that's the time base of the hydrograph. So now we need to find that. Time to peak, nope. Time to peak, time of concentration, time base of unit hydrograph. So that's that one. T sub P is the time from the beginning to the peak. Time from the beginning to the peak. T lag is from the centroid of the pulse to the peak. D is the time unit, base time of 1 unit increment. And T sub C isn't even in the lecture, but you should remember that that's time of concentration, which interestingly enough often is treated as having nothing to do with the unit hydrographs, but in fact the rational method, although imperfect, can be constructed as a very special case of a very special kind of unit hydrograph. Hit submit and tell me we're correct so we can, good. So you have to get responses correct or it won't let you out of the lesson, which admittedly is annoying, but you get to keep retrying. Hit continue and we're done with the lesson. And then we would go back to our class and tell ourselves that we've done lesson 12. Thank you for your attention and a good